So really the title itself takes 20 minutes. And an alternative title is how to compress 10 years of terribly difficult work into 20 minutes. So this is I just want to give a flavor of my work, my joint work with Michael Skyde, Michael Skyde. That's been it's been on the archive for I don't remember. Time is acting very strange now. I don't know if it's months or years, but it's recently on the archive. So we have this very long paper, 219 pages, and now I'm going to just give you a flavor. I don't have too many expectations, just to give you an idea of what's going on there. So the objects of study, before I can state the problem, what are the objects we study? We look at a semigroup. S will be a semigroup, and then T will be a family of contractive, completely positive maps on a unital, always unital, C-star algebra B. Then, T is said to be a CP-semigroup if it satisfies the semigroup property. It's the identity at 0 and it satisfies this nice property. And then just for our vocabulary, it's a Markov semigroup if it is unit preserving. It's an E semigroup if these are star endomorphisms. It's an E0 semigroup if it's a semigroup of unital star endomorphisms.
Sorry, Orr, I'm not sure if it's me, but I can only see your title slide and presumably you're already talking about something else.
That's right. I wonder why is this like happening like this? I'll stop share.
Yes, so I think other
I'll close all other windows. So thanks for so it's everyone, not only Michael. So it's my fault.
Well, there's more than one person who indicated this in the chat, so I think it's safe to assume.
I'm sharing now. What do you see now? You see my
title? So that's full screen, your title slide.
Yes.
That looks good. Can you go to the second slide?
Right. This?
Yes, that's perfect. Thanks, Orr.
Thank you. Thank you very much. So I was saying that we are talking about semigroups, families of completely positive maps T, and they are called CP-semigroups. They satisfy the semigroup property, and they're parameterized by just some semigroup of R plus to the K. You can talk about more general monoids, and we do, but just imagine that S is a sub-semigroup of R plus to the K. Markov semigroups are unit-preserving CP semigroups, and then E semigroups are endomorphic. E0 semigroups are unital star endomorphism semigroups. And the case that was of greatest interest was the case of the positive reals. And in that case, the Markov semigroups, they have quantum dynamical interpretations. So a Markov semigroup is a mathematical model for evolution in an irreversible quantum system, and the semigroup of star automorphisms is an evolution in a reversible quantum system. Here we talk, I didn't define say that I'm going to talk about semigroups of star automorphisms, but going from an E0 semigroup to a semigroup of star automorphisms is possible in many cases. Okay, so now is what we or ask whether it exists is the dilations. So dilations can mean lots of things, and in this context, this is what they mean. A dilation of T is always a CP semigroup. It's a triple A, theta, P. A is the C-star algebra. Theta is an E semigroup on the C-star algebra, and P is a projection, such that B, the algebra where T acts, is the corner of A by P, and T is obtained from theta by compression. That's the definition of a dilation I'm going to work with. And if T is unit preserving, we want the E semigroup to be an E0 semigroup, of course, because the idea is to represent a complicated object in a, say, wild category by a better understood object in a nicer category, as much as we believe that semigroups of endomorphisms are nice. We know that they're also wild. So here's a picture to have in mind. We have this T acting from B to itself, and we want to know, I mean, a dilation means that we can understand this T by first embedding B in a larger algebra, and then acting by a better behaved kind of map, and then compressing back to B. So that's the usual kind of picture you have in mind with dilation. Not always the specifics are the same. All right. So lots of people looked at this notion and studied it. And so basic questions that we can ask is to find necessary and sufficient conditions for the existence of a dilation. Or more concretely, if we fix K, then we can simply ask, does every Markov semigroup over n to the K have a dilation? So the key tool in analyzing semigroups of CP maps and then in going further is the GNS representation of a map or of a semigroup. So I warned you that I'm going to assume C-star correspondences, so no explanations here, sorry. So by the way, but I can also give you a link to a longer talk with more slides and more explanations if you like. So yeah, if we have a map, just a CP map, then there exists a unique C-star correspondence E over B and a vector C in E that recovers T like so. So it's like the GNS representation of a state, right? It looks like this, but to encode completely positive maps, you need to work with C-star correspondences, Hilbert C-star bimodules, if you like. And the way I wrote it, it's not unique. If you also that this vector spans E in this sense, then it's essentially unique up to some kind of isomorphism. Now, if you have a CP semigroup acting on B, then for every S, for each one of the maps, you have its own GNS representation. And the beautiful fact is that these things very easily can be shown to behave well with respect to one another. So for every S and T, we can try to define a map from E at the point S plus T to ES tensor ET. This tensor product denotes the internal tensor product of C-star correspondences. And we define this map the only way that we can. So E S plus T is generated by this vector and the algebra, and we send it to this guy and hope that it works. It does work. It's an isometry, and it extends to an isometry from ES plus T to ES tensor ET. And it turns out that what we get is a structure called a subproduct system. So what's a subproduct system? A subproduct system is a family of B correspondences together with a family of isometric bimodule maps which iterate co-associatively, meaning that we have this commutative diagram. Okay, so just follow the diagram with your eyes and you understand what I mean by iterating co-associatively. So it's like a semigroup of C-star correspondences. And it's called a product system when all the WSTs are unitaries. In that case, you can take the adjoints and then you have the usual picture. If you've already seen product systems, probably you've seen them with the arrow going in the other direction from the tensor to the ES plus T. So you can do that if they're unitaries. In general, you cannot do that. Okay, so these are subproduct systems. And we had another object arising there. It was a unit. What's a unit? It's a family of elements inside the fibers of a subproduct systems that behaves nicely with respect to the map. So it's a semi-group of elements in this subproduct system. So let me summarize what we have up to now and give you the basic theorem we have. So we have subproduct systems. These are roughly, you can think of them as a family of C-star correspondences that are behave nicely with respect to tensor products in this sense. And then we have the more restrictive class of product systems, where we have this identification of ES plus T with the tensor product. We also have this notion of a unit. So these are the things that we've collected up to here. And we mentioned that with every CP semigroups, there comes a GNS subproduct system and unit. So it's something that comes along with every CP semigroup. And one thing it does, it helps you to recover the CP semigroup. It knows everything about the CP semigroups. So following work by others and by ourselves actually too, we have this theorem, which is maybe the basic theorem that we obtained in our work. We actually obtained this version quite some years ago, and we have some refinements of it, but this is maybe the simplest thing to state. So here's the theorem. A Markov semigroup T on a C-star algebra B has a strict and full, never mind what these words mean, because they're in red, they mean a special kind of E-dilation. So a Markov semigroup has a certain kind of E-dilation, E0 dilation, if and only if the GNS subproduct system of T can be embedded into a product system of B correspondences. So that's what the theorem says. So that's an if and only if theorem. Let's break it apart. Let's look just at one half of the theorem. So we have this sufficient condition. So if T is a Markov semigroup, Markov means unit preserving UCP maps. And if the GNS subproduct system can be embedded into a product system, then T has a dilation. So we have a few positive results that we can prove by showing that certain subproduct systems can be embedded into product systems. We actually don't have so much, but we have some interesting results. And I want to give you the baby toy example in the context of our work. So as a corollary of this theorem, we get this theorem of Bat and Skyde from 2000, talking just about a single map. So if T is a UCP map on a unit or C-star algebra B, then it can be dilated. There exists a triple A theta P, where theta is a unit or star endomorphism such that Tn acting on B is theta n acting on B compressed. So just let's see how it's proved once we have our theorem. We need to show that the GNS subproduct system En is parameterized by whatever parameterizes the CP semigroup. So we need to show that this subproduct system of the CP semigroup embeds into a product system. So there's really only one thing you can do. You define En to be E1 to the tensor product N. You think about it, oh, it's a product system because the tensor product is associative. So this is the product system, it behaves nicely. So we know that we have these embeddings because it's a subproduct system. The GNS family is a subproduct system. But then we can take En and embed it into this tensor product. And if we continue to peel off the E1s, we end up by embedding En into E1 to the nth tensor product, which is En. So we have this embedding of our subproduct system into a product system, and it preserves the structure. This kind of co-multiplicative structure is preserved. It's not difficult to check. So this, by the theorem above, T can have a dilation. So really, this is the idea of the theorem is already going back to Butt and Skyda. Essentially, they do embed a subproduct system into a product system without saying the word subproduct system. This was just to illustrate what kind of problem you have to solve given the machinery that we've constructed. Now, in general, this never happens. This simple thing, it never happens. Not even over n to the power 2, where we can still embed subproduct systems into product systems, but it's not so easy. You have to work much harder in general. Okay, I'm going to just move on if no one speaks. Okay, so we can embed the subproduct system into a product system. We have a dilation, and a very nice one. And there's a question in the other direction: if we just have a dilation, not a very nice one, what do we get? So if T is a Markov semigroup, and suppose that we have a dilation, so it's not assumed to be strict and full. Remember, we had these words in red. It's just the simplest kind of dilation. We want to know what we get. So we follow a construction that Michael invented almost 20 years ago, and we define a family, ES, of B correspondences as follows. We hope that it's going to be a product system. Let's see what happens. So we define E to be this Hilbert module, and then we have these spaces, and on these spaces we define a C-star correspondence structure. The left multiplication is defined like so. The right multiplication is defined like so. And we have an inner product defined in the natural way when your module is a subspace of a C-star algebra. This is the inner product. And we define something that we hope is going to turn out to be a unit. Eta S is defined like this. So we have all these ingredients, and we're trying to construct something that behaves nicely. This eta S, what does it do? So if we calculate B acting on eta S, inner product eta S, follow the above, we see that we get this by the properties of theta, and then that's just TSB because we assume that it's a dilation. So this pair, module and vector, represent our UCP map, like so. So let's see what we have. We started from a Markov semigroup. We have a dilation. We construct some family of modules, B correspondences, and these vectors, and they recover T in this way. So that means that this module contains the GNS representation of the semigroup. Because the GNS representation is unique, it embeds into every pair that represents T like so. And then the question is whether it's a product system. If it's a product system, then we're done. I mean, we showed that a dilation, just a simple dilation, implies the existence of a product system. And the answer is that this is not always the case. The life is very complicated. And the dreams you have for an if and only if theorem are not always going to come true. But then there are nice surprises because it's not a product system, but there's another structure going on here. We can define maps from the tensor product to EST, these product maps, that take a tensor product to this product. And a direct calculation shows that these are, now, these ideas don't come out of the blue, okay? We didn't just try things. They come out of what was true for module dilations. So they come from the literature, and we explain that in our paper. So this is a superproduct system. When we have isometries going this way, it's a superproduct system. So let me just say what it is. A superproduct system is a family of B correspondences together with a family of isometries that iterate associatively. We have this commutative diagram, and it's a product system is a superproduct system where the VSTs are all unitary. This coincides with the previous definition of product system coming from as a special case of subproduct systems. So never mind this remark. So let's recap what we have. We have subproduct systems, product systems, units. Now we also have superproduct systems. And the subproduct system is something that comes with every CP semigroup. And the superproduct system is something that comes with every dilation. So the theorem that I want to kind of break up is like this. If we have a Markov semigroup on a C-star algebra, then a sufficient condition for T to have a strict and full dilation as before is that the GNS subproduct system of T embeds into a product system. That's the theorem I had before. Yeah, and now the question is, if we have just a dilation, not a special kind of dilation, then what's the necessary conditions for that? It's that the GNS subproduct system embeds into a superproduct system. That's the theorem we have. And then we are left with some open problems that we don't know. For example, if the GNS, if we can embed the GNS system into a superproduct system, does it guarantee the existence of a dilation? And does the existence of a simple dilation imply the existence of a strict full dilation? Or can every superproduct system be embedded in a product system? If we knew that, then we'd be able to show, we'd be able to close the circle. We'd be able to show that the existence of a dilation implies the existence of a strict full dilation, but we don't know that. And with these open problems, I stop talking. Thank you very much.